Have you ever wondered how astronomers link a momentary glance at the sky with eternal cosmic coordinates? The answer lies in the parallactic triangle, which connects the celestial pole, the zenith, and the distant luminary. Special trigonometric formulas make it easy to convert volatile horizontal star coordinates into stable equatorial ones. It is this remarkable geometry that has become the true heart of all modern practical and fundamental astrometry.
Have you ever stood under the night sky, looked up at a single point of light, and truly considered the problem? We are on a moving platform, a spinning planet, looking out at what appears to be a fixed, grand sphere of stars. So, how do we connect the two? The answer, it turns out, is a remarkably elegant piece of geometry known as the parallactic triangle. I want you to think of it as a celestial Rosetta Stone, the master key that translates the language of our local sky into the universal language of the cosmos. Let's delve into exactly how this works. So, here's our roadmap. First, we'll establish the fundamental problem that every astronomer faces. Then, we'll actually build our solution, the parallactic triangle, step by step. After that, we'll dissect it, looking at what each side and angle really represents. We'll then see how this geometry gives us the powerful transformation equations we need. And finally, we'll understand why this single triangle is absolutely central to the science of astronomy. You see, any observation of the heavens begins with a fundamental conflict. We, as observers, are stuck in a very local frame of reference. We have a horizon, a point directly above our heads, and a compass. The stars, on the other hand, belong to a much grander, seemingly fixed framework, the celestial sphere. The entire challenge, then, is how to bridge these two completely different coordinate systems.
So this is the central question, isn't it? How do we take the measurements we can actually make right here, right now, like a star's altitude above the horizon and its azimuth, its compass direction, and convert them into a universal set of coordinates that is valid for any observer anywhere on Earth? The solution isn't just about plugging numbers into a computer. It's a deeply elegant geometric insight.
And that solution is a geometric construct, a specific shape drawn right onto the surface of the celestial sphere. So let's build it. We're going to construct the parallactic triangle, step by step, to see precisely how it forges the link between the observer and the star. All right, I want you to visualize this. Picture yourself standing in a vast, dark field. The sky is a perfect dome above you. That's our celestial sphere. Now we need 3 critical points. The first is easy, your zenith, which we'll label Z. That's the point directly over your head. The second is the celestial pole, P. This is the pivot point of the heavens, the projection of Earth's axis into space, along which all the stars seem to wheel. And finally, our third point, M, is the star itself. These 3 points, Z, P, and M, will become the corners, the vertices of our triangle. Now we connect the dots. But remember, we're on the curved surface of a sphere, so we don't use straight lines. We use the shortest possible paths, which are called arcs of great circles. As we trace these arcs from your zenith to the pole, from the pole to the star, and from the star back to your zenith, a triangle materializes on the celestial sphere. And there it is. That is our parallactic triangle. It creates an unbreakable geometric relationship between you, the Earth's axis, and that star.
Now, for the formal definition. The parallactic triangle is a spherical triangle formed by the intersection of 3 key circles. The side connecting your zenith and the pole, ZP, is a piece of your celestial meridian. The side from your zenith to the star, ZM, lies along the star's vertical circle. And the third side from the pole to the star, PM, is a segment of that star's hour circle.
So, now that we've built it, let's take it apart and see what makes it tick. Each component of this triangle isn't just an abstract line. It corresponds to a very real, very meaningful astronomical quantity. Let's start with the 3 sides. Let's look at the first side, the one connecting the zenith, Z, and the celestial pole, P. It's a fundamental fact that the altitude of the pole above your horizon is exactly equal to your geographic latitude on Earth, which we call phi. Well, your zenith is, by definition, 90 degrees above the horizon. So the distance from your zenith down to the pole has to be 90 degrees minus your latitude. We call this the colatitude. Okay, next side. The one connecting your zenith, Z, to the star, M. This one's pretty intuitive. It's simply the star's zenith distance, Z, the angular gap between the star and the point directly overhead. This is the direct complement of the star's altitude, H, which is what you'd measure from the horizon up. So Z is simply 90 degrees minus H. And the third side connecting the celestial pole P to the star, M. This is the star's polar distance, P. It's analogous to latitude on Earth. In the sky, a star's position north or south of the celestial equator is called its declination, or delta. The polar distance then is simply 90 degrees minus that star's declination. All right, we've handled the sides, but every triangle also has 3 interior angles. And just like the sides, each of these angles maps directly to a critical astronomical measurement. They are the final pieces of the puzzle. Let's start at the top with the angle at the celestial pole, P. This is the star's hour angle, denoted by T. The hour angle is essentially a celestial timekeeper. It measures how far the star is in an east-west direction from your local celestial meridian. In other words, it tells you how long it's been since that star was at its highest point in your sky. Now let's move to the angle at your zenith, Z. This angle is directly tied to the star's azimuth, A, which is just its compass direction. For any star that's in the western half of the sky, this internal angle of the triangle is equal to 180 degrees minus its azimuth. This gives us the crucial link to the star's bearing along your horizon. And finally, the third angle, the one located at the vertex of the star itself, M. This is known as the parallactic angle, Q. Now, this one can feel a bit more abstract, but it is critically important for high-precision astronomy. It essentially defines the orientation between the star's vertical circle and its hour circle, and it's indispensable for making corrections for things like atmospheric refraction. So let's pause and appreciate what we've just done. We have assembled a single geometric figure where every single side and every single angle is defined by quantities from both the observer's local system and the star's universal system. And because of this, we can apply the mathematical laws of spherical trigonometry to derive equations that let us translate between these two systems with absolute precision. So what's the first major application? Well, imagine you're an observer. You've just made a careful measurement of a star's position in your sky. You have its zenith distance and its azimuth. Using the relationships we just defined in our triangle, you can now calculate its fixed universal coordinates, its declination, and hour angle. And here they are. This is the machinery that makes it all happen. Now, don't worry about memorizing these formulas on the spot. What's crucial is to understand what they do. They are the engine of our Rosetta Stone. You input your known quantities, your latitude on Earth and the star's measured zenith distance and azimuth, and these equations output the star's permanent address in the cosmos. This is how we convert a fleeting local observation into a point on the universal map. But what's really powerful is that this works both ways. Let's flip it around. What if you already know a star's universal coordinates from a star catalog? The parallactic triangle lets you work backwards to predict exactly where that star will be in your local sky at any specific time. And these are the corresponding formulas for prediction. This is the bedrock of all practical predictive astronomy. This is how we calculate the exact time of sunrise for any location on Earth. It's how a modern telescope knows precisely where to point. And it's how sailors navigated the oceans for centuries. We are taking the universal map and projecting it onto our personal, local reality. And all of this brings us to the profound significance of this one shape. The parallactic triangle is not just some clever mathematical tool. It is the conceptual and computational heart of astrometry, which is the science of precisely measuring the positions and motions of everything in the sky. This quote just says it all, doesn't it? It perfectly captures the essence of the triangle's role. It is the non-negotiable bridge between the observer's subjective reality, the here and now, and the objective, fixed reality of the cosmos, the where it is on the universal grid. So the power that this one triangle unlocks is just immense. It's what allows us to take observations from Earth and build precise star charts. It's what lets us predict eclipses and transits with minute-by-minute accuracy. It provides the entire mathematical framework for celestial navigation. And it remains, to this day, an absolutely essential tool for astrophysicists who need to untangle an object's true motion from the motion of the Earth itself. So the next time you're outside on a clear night, I want you to look up at a star and picture that invisible triangle hanging in the sky, connecting you, the pole, and that distant sun. It's a powerful testament to how pure geometry can decode the universe. That one elegant spherical triangle is the key that truly unlocks the clockwork of the heavens and allows us to find our place not just on our own planet, but in the cosmos.
Thank you, friends. Strive for understanding and become wiser. See you soon.